Hello, everyone. I'm Professor Sodao Peng. I'm from the Southern Taiwan University of Science and Technology. Today, I'm going to talk about my topic, the enhancement of your moment control with active steering saturation for drivers panicking in emergency then change. These are the contents of our topic: motivation, lateral control model, and safety references enhanced your moment control, including active steering saturation control, your moment constraint and wheel torque distribution, your moment control design, and I will demonstrate some simulations and give you my conclusions. Motivation. The front steering angle significantly affects the lateral stability of vehicles in high speed. A slight axis of the angle can immediately result in the vehicle sliding sideways and out of control. The conventional integration of active front steering and directional moment has the advantage of delivering promising stabilization performance, but it has the drawback that when the vehicle is operating near the friction saturation zone, the integration may risk excessive steering with the combined FS. In the case of vehicle operating near the saturation zone, mostly the literature uses the DYM alone and regards the driver's excessive steering as an external disturbance. As a result, less capacity of the yaw moment can be left to tackle other instability factors. This study presents an enhanced yaw moment control in which a scheme is used to directly block the driver's excessive steering, like the FS, through the coupling function of the planetary gear mechanism. The approach allows the enhanced yaw moment control to have more capacity left to cope with other instability factors, even when the driver's steering angle stretches beyond the stability range. A type of diaphanal-based robust control is employed to generate the enhanced yaw moment and ensures its magnitude is within a pre-specified range to prevent the creation of excessive wheel slip. Lateral control model and safety references. We consider a ground vehicle running at a constant speed v0. The lateral control model we use in this study is this matrix differential equation with detailed matrices AV, BV, BM here. The system state contains the side-slip angle beta and yaw rate gamma. Delta F is the front wheel steering angle. BZMC is the yaw moment used for control, which is mainly generated by the longitudinal tidal friction forces of the four wheels. dV is the uncertainty vector representing the modeling errors and disturbances. The system output we present here contains the lateral acceleration of the center of gravity, AY, the front wheel slip angle, alpha F, the rear wheel slip angle, alpha R. In this lateral control model, the vehicle system matrix AV is asymptotically stable in the range of allowed speeds, and the matrix pairs AV-BV, AV-BN are controllable. The vehicle reference model we use in the study is represented here. To construct this vehicle reference model, the wheel steering angle in the vehicle lateral control model is regarded as the driver steering angle, and the matrices dV and mz of 0. The vehicle reference model have the steady state here, and the steady state of this reference model is used for defining the safety reference state. This is the flow diagram of the steady state relationship from the driver steering angle to the steady state of yaw rate, lateral acceleration, side slip angle, and the front wheel slip angle and the rear wheel slip angle. The notation K here is the vehicle stability factor. Construction of the safety references. That is a safety restriction given in the literature on the steady state lateral acceleration. The restriction is given here. Mu max is the maximal tire friction coefficient, and G is the gravity constant. And based on this safety restriction, we can inverse the flow map to find out the related limits on the driver steering angle, the yaw rate, the side slip angle, the front wheel slip angle, and the rear wheel slip angle. Okay, based on these related limits, we can define the safety reference state and the reference steering angle as these three equations. And also we can define the reference operational ranges of the front and wheel slip angles as these two inequalities. And we can see that the safety reference state and the reference steering angle satisfy this matrix equation. Enhanced yaw moment control. Active steering saturation control. The study uses the planetary gear mechanism to implement the steering saturation scheme. This mechanism redefines the wheel steering angle as the combination of the driver steering angle and the saturation angle. The saturation angle is used to curb the excessive driver steering angle. The control of the saturation angle is proposed with this dynamical equation, where the notation is the reference steering angle, which is derived from the steady state of a reference model. Omega d is the angular speed of the driver steering, and the alpha here is chosen sufficiently large such that the saturation angle can be regarded as much faster in comparison with the driver steering angle. Therefore, the dynamical equation of the front wheel steering angle turns to be this equation. And suppose alpha is sufficiently large, and the initial condition of the front wheel steering angle is close to the reference steering angle. In this condition, the wheel steering angle can be viewed as the reference steering angle, with their difference being sufficiently small. Let the error be the difference between the vehicle state and the safety reference state, and the aerodynamical equation can be obtained as this matrix differential equation. And in this equation, the total disturbance can be expressed as this. Now, if only the yaw moment is employed, that is, the saturation angle is not used, in this case, the disturbance nu can be obtained as this equation. We see that this disturbance nu increases with the growth of the driver steering angle, as the driver steering angle stretches beyond the limit on the steering angle. If the saturation angle is deployed, and in this case, the disturbance nu can be regarded as sufficiently small. In this way, the excessive driver steering angle can be blocked, and therefore the related disturbance nu almost vanishes. So most capacity of the yaw moment mz can be left and used to keep up with the safety reference state and to tackle other instability effects. Even the driver steering angle stretches beyond the limit on the steering angle for a while. Yaw moment constraint. The study considers the yaw moment to be generated under the restriction of the wheel slip to prevent the creation of excessive yaw moment that can cause undesired wheel skid and risk the loss of maneuverability. As we know, when the vehicle state and the front wheel steering angle remains smooth, the yaw moment can be approximated as this equation. Therefore, based on the faster wheel dynamics, the traction brake force of each wheel when operating in the linear tire friction region can be replaced with its quasi-steady state as this equation, where Tz is the wheel torque, Re is the effective radius, Fz is the wheel normal load, Kz is the slope of the tire friction coefficient, and SL is the longitudinal wheel slip. We assume that during the process of the active safety control, each wheel has the same tire friction characteristics and is engaged with the same amount of longitudinal wheel slip by the wheel torque control, which means each wheel has the same slope of the tire friction coefficient and the same longitudinal wheel slip. When the yaw moment direction is determined, the wheel control torques assigned to the four wheels are proposed as these four equations. And therefore the related longitudinal friction forces become as these four equations. So the magnitude of the yaw moment can develop into this equation, and we can see that the magnitude of the yaw moment can reach its maximum allowable amount when the longitudinal slip also achieves its allowable limit. So we can obtain the restriction on the yaw moment as this inequality. Now we consider the estimate of the yaw moment restriction. We use the concept of the friction circle restriction here. And this notation is the allowable magnitude of the combined wheel slip that does not make the tire friction saturate. And this is the operational range of the lateral wheel slip needed in the reference following control. The selection of this depends on the road conditions. For example, 0.1 can be used for the drive actual road condition, and 0.08 can be used for the weight actual road condition. The range of this is estimated using the information on the steady state wheel slip angles and is considered to be this equation. Yaw moment control design. According to the matrix BM in this aerodynamical equation, we choose a matrix BMC such that their combination is of full column rank. And the overall disturbance can be decomposed into this representation. And their coefficients satisfy these two inequalities. We use the concept of the Lyapunov-based robust control to design our yaw moment control, in which the matrix P is symmetric and positive definite, which satisfies the Lyapunov equation here. And we can see that the yaw moment control satisfied the pre-specified constraint. Stability analysis. If we use the state feedback yaw moment as the input to control this aerodynamics, then we can obtain the closed-loop aero system as this. We consider this is to be the diagonal function candidate. Then the derivative of the diagonal function along the trajectories of the closed-loop error system satisfies the inequality here if the norm of the error is greater than this value. So the closed-loop error system is ultimately bounded and practically stable. To prevent the control childlink, we modify the original control into this form, in which the epsilon is chosen sufficiently small. In conclusion, the overall integration control contains active wheel steering saturation and four-wheel control torques here. And the control torques is derived from the yaw moment control. Simulations. Demonstration in comparison. We compare the vehicle performances under the integration control and the active along yaw moment control, in which both the yaw moment schemes use the same parameter values. Driving condition. The control scheme is tested with a nonlinear vehicle model, D-class sedan in the car-themed Simulink co-simulation environment. And we assume the driver makes an emergency lane change on a drive asphalt road with the vehicle at speed 120 kilometers per hour. The vehicle parameters and limits on the associated references are listed in this table, and the design parameter values are given here. We use this time function as the time response of the driver's steering angle, and this time response is illustrated in this figure here. These two red lines represent the limit on the driver's steering angle. These figures demonstrate the time responses of the vehicle state and the related accelerations without the safety control. We can see the vehicle begins to slide and lose maneuverability from about 1 second. The effectiveness of the saturation angle. The figure below demonstrates that saturation angle can effectively make the front steering angle behave as we propose in this equation. We can see the front steering angle is sufficiently close to the reference steering angle. Comparison of the two yaw moment schemes. The time response of the acting along yaw moment control is depicted here in blue. We can see that the acting along yaw moment control needs to generate a significant yaw moment in these two periods to suppress the instability effect produced by the excessive driver steering. And the time response of the yaw moment of the integration control is depicted here in black. And we can see that the yaw moment of the integration control largely acts in these three intervals, during which the driver steering angle changes rapidly for the emergency lane change. So it means that the enhanced yaw moment control only needs to focus on its main task of safety reference following control. The resulting vehicle state of the integration control and that of the acting along yaw moment control are depicted in these two figures. We can see that both of the control schemes have their state confined near the safety reference state. The acceleration of the integration control and that of the acting along yaw moment control are depicted in these two figures. We can see that during the lane change, both of the control schemes have their lateral accelerations kept within the limit range of 0.85 g. The resulting wheel torque schemes of the integration control and that of acting along your moment control are depicted in these two figures. We can see that for the acting along your moment control, much more wheel torques are needed to offer during the emergency than change. The corresponding magnitudes of the combined wheel shifts of the four wheels are depicted here. We can see that significant coexistence of the longitudinal and lateral slips of the two front wheels takes place in these two periods, during which the acting along your moment takes on the excessive driver steering. In this situation, the friction forces of the two front wheels are near the saturation region, and the force have little capacity left to tackle other stabilization issues. In comparison, the proposed integration scheme, as shown in the left figure, prevents the drawback of the significant coexistence. Remarks. While the acting along your moment control still retain the safety and stability of the vehicle during the emergency lane change, part of its stabilizing capacity must be deployed to suppress the instability effect of the driver excessive steering, thus weakening its ability in coping with other stabilization factors. Conclusions. We have presented an enhancing scheme for the conventional your movement control that is often used in the case of drivers steering too much in panic. The scheme allows the enhanced your movement control to have more capacity left to tackle other stabilization factors, especially as the driver steering angle stretches too much. An estimate of restriction on the yaw moment has been proposed, and using the estimate, we can construct a diaphanous-based robust control scheme that ensures the raw moment can be delivered in the restriction range to prevent creation of excessive wheel slip. Thank you for your attention.